Hi everybody, and welcome back to my lecture series on hardware for deep learning. I'm Dr. Adam Teman of EnICS Labs at Bar-Ilan University, and today we'll be going over Part 3, Computing Convolutions. This lecture has 4 parts. We'll be starting with the part called Mapping Matrix Multiplication. So remember, deep convolutional neural networks are these very large, long networks that have many layers of these convolutions, right? There are so many convolutions here that actually it's been shown that convolutions account for more than 90% of the overall computation, dominating runtime and energy consumption. It's a whole bunch of these nested loops that have to do these convolutions all over the input feature maps. So convolutions are just dot products. Well, here we have an input feature map of 5 by 5 on the left, and here we have a filter of 4 by 4 on the right. And actually, what we can do is just map this type of a convolution where we take the window of interest over here, we'll flatten it out so we have ABFG going into a flattened vector over here, and we take our filter and we'll flatten ABCD into a column vector, and then we can just do a dot product between them, and we get the output is A times A plus B times B plus F times C plus G times D, and that's our dot product of one slide of the window over the input map, and we have to do this many times over the whole thing. Well, also let's look at what we have here. We basically have a multiply and accumulate operation. So this one 4 by 4 dot product is just 4 times multiplying two scalars and summing them up with the previous. So it's a multiply and accumulate. In fact, this type of 4 by 4 dot product is made up of 4 MAC units, multiply and accumulate units. Okay, so we have 4 MAC operations. It's actually much easier if we would kind of rearrange our matrix to do this in a nice way and do it with a simple matrix multiplication. So we can convert our input matrix to what's called a Toeplitz matrix, and this enables a matrix multiplication for the entire convolutional layer. So here we have our input map, and here we have our filter, and we're going to slide this 2 by 2 filter over this 3 by 3 input map. It's going to have 4 spaces. So here's the green one, the blue one, the red one, and the purple one, and they correspond to the green, blue, red, and purple output maps. Well, that again would be making 4 dot products. But what we can do is we can just actually rearrange our input map, and instead of having it like it was, we can make a new matrix that now has A, B, D, E, B, C, E, F, D, E, G, H, E, F, H, I. And what happens is A, B, D, E times A, B, C, D here is exactly this first convolution over here. So it's our green output, which we called 1, 1. And for example, the last one is E, F, H, I times A, B, C, D. That's exactly E, F, H, and I times A, B, C, and D. That's our purple one. So just by rearranging our input feature map, we can make one matrix multiplication here and get our entire convolution of sliding windows. We should pay attention though that this increases the size of our input map, and in this small example it increased 3 by 3 input map to a 4 by 4 input map, and that's because we have several of these input values that are redundant, right? We have B appears twice, and D appears twice, and E appears 4 times, F twice, and H twice. So we're paying with some some redundant values, but we're able to now optimize the operation to do it in one shot. How does that work with multiple input channels? So now we have 2 input channels we have 2 input channels in our input feature map, and then we have 2 filter channels that they have to multiply by. And of course, the first slide of the window puts the filter 1 over input channel 1 and filter channel 2 over input channel 2, and together the dot product of all those 8 values gives us this 1, 1. Well, it's pretty easy to do with the Toeplitz matrix. We just take the Toeplitz matrix of input channel 1 and that of input channel 2, and we put them side by side, and then we multiply it by a column vector that's just the filter channel 1 on top of the filter channel 2, and that exactly gives us this 8 by 8 dot product, gives us each one of these output values. What about if we have multiple output channels, which is actually multiple filters? So again, we have our side-by-side Toeplitz matrices of our multiple input channels. and we have our filter, our first filter that's one on top of the other, and that gives us the output channel 1. Well, now we just need to take our second filter and also put it there with each channel on top of the other, and it gives us output channel 2. So these Toeplitz matrices are a nice way of reorganizing our data that gives us a matrix multiplication to solve our convolutional layers, and several software packages can map these conversions. These include OpenBLAS and Intel MKL for CPUs, and CuBLAS and CuDNN for GPUs. So with that, we can go over to our next chapter, which is called computational transforms. So multiplications are a very expensive operation. They're much, much, much more expensive than additions. And so what is often done is we apply some computational transforms to our matrices to get less expensive operations or more additions than multiplications. The three that I'm going to discuss are the fast Fourier transform, or FFT, and then Winograd's and Strassen's algorithms. So let's start with the fast Fourier transform. So convolution can be computed using an FFT, and it's pretty simple. All we do is we take a convolution, which is the x convoluted with the w here, the input convoluted with the filters, and if we transform it with an FFT, we just have a simple multiplication, and then we can do the inverse FFT to bring it back into our original field. Okay, so we convert the filter and input to the frequency domain to make a convolution, and simply multiply and then convert back to the space domain. So we're going to take our input map, we're going to run an FFT, and we're going to get the FFT of the input map. We're going to take our filter, we're going to run an FFT, we're going to get the FFT of the weights. We're going to just multiply these simply, get the FFT of the output, then we're going to run an inverse FFT, and we'll get our output FMAP. And that seems like it would be a much simpler computation than doing our whole convolution. Actually, this reduces the complexity from here, the size of the output squared times the size of the filter squared, to something like size of the output squared and log of the size of the filter. That's supposed to be an F. Okay. So benefits of fast Fourier transform are obviously that it reduces the complexity, and the larger the convolutional kernel, the better the performance of this. As we saw there's the log of the size of the filter. However, filter sizes are often small. We discussed that filter sizes are often like 3 by 3, 5 by 5, and if they're small, we're losing this benefit. The other thing is that coefficients in the frequency domain are complex, and therefore the calculation becomes more complex. And also, we have very sparse matrices, and once we do this FFT, we lose a lot of the sparsity, and we can't exploit it as much. Okay, so FFTs, they often reduce the computation, but they require much more memory space and bandwidth to do anything. There are, however, many optimization opportunities. For example, the FFT of the real matrix is symmetric, so we can only do half of the computes, which is really nice. The filters can be pre-computed and stored, so we can do this FFT of the filters beforehand, but the filters in the frequency domain are large, so this is going to be larger. We can also reuse the FFT of the input maps for creating different output channels, and we can accumulate across the channels before doing this IFFT. So there are many opportunities for optimization, and fast Fourier transform has been shown to be one way to do these convolutions efficiently. However, the more common ways of applying these types of computational transformations are Winograd and Strassen's algorithms. So just to get a background for this, I'm going to take a look at Gauss's multiplication algorithm, which is kind of a simple case of one of these. So if we take A plus BI times C plus DI, we know that it equals AC plus BD plus BC plus ADI. And if we look at this thing, there's 1, 2, 3, 4 multiplications and 1, 2, 3 additions. So it's four multiplications and 3 additions to get this. However, we can make this simple kind of a transformation. So K1 equals C times A plus B, K2 equals A times D minus C, and K3 equals B times C plus D. So here we have 1, 2, 3 additions, subtraction is like an addition, and 1, 2, 3 multiplications. right? Now, once we have these median values, the real part is just k1 minus k3, so that's another addition, and the imaginary part is k1 plus k2, so that's another addition. So altogether, we got 1, 2, 3, 4, 5 additions and 3 multiplications. So that means we have a few more additions, but additions we said are much cheaper, and we were able to get less multiplications. So that's kind of the basic type of transformation we're going to do, and let's see how it works kind of on Strassen's algorithm. So Strassen's algorithm has been shown to reduce the complexity from O n to the third to O to n to the 2.807. Okay, how does it do this? We take an A matrix and a B matrix here, A, B, C, D times E, F, G, H, and we get the C matrix, which is over here, and this is a total of 8 multiplications, 1, 2, 3, 4, 5, 6, 7, 8, and 4 additions. Okay, we can, again, make these partial kind of computations, so P1, P2, P3, P4, P5, P6, P7. Each of these is a multiplication. Well, each of this side is a multiplication and addition. Each of these side is a multiplication and 2 additions. And using those, we can rewrite the C matrix to be P5 plus P4 minus P2 plus P6, etc., etc. And if we look at this, it's a total of 7 multiplications and 18 additions. So we, again, were able to reduce a multiplication at the expense of many more additions. But if the B matrix is constant, which it will sometimes be, for example, with filters, then we can reduce the number of additions heavily. So this actually comes at the price of reduced numerical stability and requires significantly more memory, but it is one way to reduce the number of multiplications that we do. The more popular way is using the Winograd algorithm. I'm just going to show here a one-dimensional version of Winograd called F23. So F23 targets convolutions instead of matrix multiplications, and the notation is F, the first number, the 2 over here, is the size of the output, and the second number is the filter size. Okay, so the size of the output is here, and the filter size is over here, and so F23 would be taking an input with 3 columns and 2 rows, multiplying it by a 3-weight filter, and we get 2 outputs. If we look at this, this is a total of 6 multiplications and 4 additions. So what we're going to do is we're going to apply this to blocks of the input, and we're going to instead write M1 plus M2 plus M3 as Y0 and M2 minus M3 minus M4 as Y1, and here are the expressions for M1 through 4. And if we see that, it's 4 multiplications, 12 additions, and 2 shifts, and even less for a constant weight. So we were able to save quite a bit here. Okay, and if we look at the Winograd in 2-dimensional, it's just nested 1D Winograds into a 2D Winograd, and this is really nice because the original in this case is 36 multiplications, and when we got it to Winograd, it was reduced all the way down to 16 multiplications, and that's a 2.2x reduction. So it's really a nice type of a thing. The only problem is each filter size and output size is a different computation, so we need some specialized hardware for that. Anyway, applying these types of computational transforms is a nice way to reduce the number of multiplications that we have in our problem. Okay, that brings us to the third part of our lecture today, which is called accelerator architectures. So we have a memory access bottleneck. Let's look at that through what a MAC is. So we saw that MACs are the basic operation that we need for these dot products, which make up our convolutions or our matrix multiplications. And what is a MAC, basically? And here we see it on the side. It's a multiplication and an addition. So what we're going to do for a MAC is we're going to read the filter map activation. We're going to read the filter weight. We're going to multiply these two guys together, right? We're going to read the partial sum that we had from before. We're going to add that to our product of our filter weight and activation, and what we get we're going to write back into the partial sum again. So that's quite a bit of stuff, right? So we needed several accesses. We needed 3 read accesses and 1 write access for every single MAC. Okay, so that's 4 memory access for every single MAC, and AlexNet, for example, would have needed 3 billion memory accesses per inference. That is quite a lot, 3 billion of them. Okay, in the worst case, if each memory access goes to DRAM, that's going to be really bad because DRAM accesses are much slower and much higher energy than the computation itself. So we want to not go to DRAM. That's, I guess, a given. That's a clear thing. For example, what we do with caching and so forth in standard computer architectures. So we don't want to use DRAM. Okay, so how are we going to do that? We're going to leverage local memory. We're going to put some sort of buffering, some sort of memory hierarchy between the DRAM and the Mac in terms of both reads and writes. So extra levels of local memory are smaller. So these memories are much smaller than the DRAMs, but they're going to be faster and much more energy efficient. So that's the basis of what we're going to do. Okay, and the other thing is we want to leverage parallelism for our higher performance. Okay, so whatever we read from the DRAM, we want to store in a memory, and if we can, we want to send it to many of these different computational units and do things in parallel, and that will increase our bandwidth or our throughput. So there's two basic categorization into two types of highly parallel compute paradigms that Vivian Z has made in her MIT tutorial. And the first one over here is called the temporal architecture, and that's used by SIMD and SIMT type architectures, and we'll explain it in a second. And the second one is what we call data flow processing or spatial architectures. So starting with the temporal architecture and just touching on it, again, this is what we have in CPUs and GPUs. So we're going to improve parallelism through vectors, SIMD, single instruction multiple data, or parallel thread, the single instruction multiple threads, which is used in GPUs. So we have centralized control. So we have the big control over here, which controls a large number of all these ALUs, of all these computational units that are somewhere, and we have a register file that is shared by everybody. Okay, the ALUs can't communicate directly through between them. Okay, since these are these big operations of matrix multiplies and stuff, and they're very good at doing matrix multiplies, we're going to use the computational transformations such as we saw before on the kernel, and this can reduce the number of multiplications to increase throughput. But if we are making an ASIC or using an FPGA and we're making custom hardware, we can actually use data flow processing to bring ourselves to what we call a spatial architecture, and then we can do something much more efficient. Okay, so now we're going to put ALUs, that these ALUs are some sort of processing chain. And each ALU, which we're going to now call a processing element, okay, it's going to have its MAC inside or whatever type of computation it's going to run, but it's also going to have some sort of local storage and some sort of control. Okay, so an ALU plus local memory is called a processing engine, and this can increase the data reuse from low-cost memories to reduce the energy consumption. So let's see how multi-level low-cost data access works. Okay, we're going to have a large global buffer that's going to get its data from the DRAM. Okay, we're going to have a large global buffer over here that's going to get its data from a DRAM. It's going to be hundreds of kilobytes. Okay, and then we're going to have this processing element network that's going to pass things between the ALUs, and the ALUs are each going to have a few kilobytes of memory locally. So data from the register file inside the ALU or from a local P is much, much more energy efficient than DRAM access. So DRAM is going to be 10 to the 6 larger storage, but it's also going to be at least 100 times more energy wasting than on-chip memory. So we see that from the ALU itself, from the register files, which are pretty small, it's not going to be a lot of energy. Coming from an adjacent PE, it's going to be a bit more energy, but coming from the buffer, it's going to be quite a bit more energy, but coming from DRAM is going to be several orders of magnitude more energy. So we're going to try to reuse the data that's fetched from the DRAM so we don't have to keep on going back and getting more and more of this expensive stuff. So we have a categorization of 3 types of data reuse opportunities in DNNs. Okay, the first one we call convolutional reuse. Convolutional reuse means that we're going to be doing convolution, so we want to try to reuse both the activations and the filter weights in order to not waste energy doing on data fetching and storing while doing convolutions. Feature map reuse, okay, that's we're going to try to reuse the activations. Okay, and while convolutional reuse is only really good for convolutional layers and not really for fully connected layers, feature map reuse is relevant for both of them. And the third one is what we call filter reuse, where we're going to try to reuse the filters, and it's good for both convolutional and feature and fully connected layers, but only when we're running batches during training. And that brings us to the last section of our lecture, and the longest section, which is about data flow taxonomy. Okay, so to manipulate data reuse in the spatial architecture, which we showed above, there are several. There's another categorization into about 5 types of data flows that can be used: wait stationary, output stationary, input stationary, row stationary, and no local reuse. So just to get ourselves on the same page, we have our Mac over here in the middle, and we're going to have our processing element is going to encompass a wait buffer, an input activation buffer, and an output activation buffer. Okay, and the Mac is going to have to do accumulation, so it has to read the partial sum, and what it's going to want to do is, what it's going to do is going to want to read the partial sums from the output activation buffer. And what we have to realize here is that the storage here is very small. Okay, so in all of our examples, which are going to be really small toy examples, we're going to be limited by how much memory we actually have in these registers that are close to the Mac. So let's start with the wait stationary data flow. Wait stationary is going to try to minimize the energy of reading weights. Okay, reading weights, it means we're going to try to maximize the convolutional reuse and filter reuse of weights. Okay, how does that work? So weights are read into the register file of each PE and kept there. Okay, so we're going to have the weights kept inside the PEs, as you can see here. Okay, we're going to run as many Macs as possible that are going to be using the same weights while it's stored in the register file before changing it out. Okay, but we also need the input maps and the partial sums. So the input maps or the activations are going to be broadcast to all of the PEs, and the partial sums we're going to try to move it spatially across the partial processing element array. So just as an example of one of these types of papers that's come out, it's actually a pretty old paper from all the way back in 2009, even before AlexNet, and this is the new flow convolution engine, and it used wait stationary to do its computations. And another one of those is a more recently released NVDLA open source project from NVIDIA. And here you can see we have these convolution buffers. That's the global buffer, and we have the convolution core, which is these PE arrays. And as you can see here, kind of in the little picture over here, what it's doing is this wait stationary, like we showed before. So let's go kind of into the mechanics of this wait stationary data reuse. What we're going to do is keep the current weights inside the register. Okay, so what we can see here, everything that I have marked here in red is in the register. We have our input maps, okay, and it has several channels. We have the filters, which each have the same number of channels. Right here we just show 3, but it can be any number. And we have several filters, so we have output maps that the number of channels in the output is similar to the number of filters. And so what we're going to do again is we have limited storage in our processing element, and we want anything that's read here is inside the processing element. So in this case, we have room to hold these inputs in the processing element, all of these weights in the processing element, and these outputs in the register file of the processing elements. So what we're going to do is we're going to keep our weights in the register. So we're going to keep these guys, hopefully. Okay, and we're going to cycle through the input and output feature maps. So the input, these guys we're not going to be able to keep, and these guys we're not going to be able to keep. The input and output F maps and partial sums. So let's see how this works. Okay. So we start here with this first coordinate of our filter, okay, and we don't want to swap it ever. So we have now stored we've stored our first coordinate of our input feature map into here, and we're going to multiply, we're going to multiply these 3 guys by these 3 guys, and by these 3 guys, and all of these, the top left value in the weight filters, and that's going to give us the first value that's going to be stored in our output map. Now what we want to do is, again, we don't want to change the weight that's held here in the filter. So what we're going to do now is we're going to throw away what we have in our input, and we're going to go over to the top left corner of the next sliding window. Okay, and the top left, so we threw away, we had A stored, now we're going to load B into the register file, and B is going to multiply by the filters over here, but the partial sum that comes out of it is going to be stored here in coordinate 1, 2, not in 1, 1. Okay, and similarly, we're going to go to D and then to E. Okay, but each of these are all the top left corner of our window of interest, so they're going to be multiplied by the same weight. Now, basically, we have finished using this weight number A, and we can throw it out and load weight number B. Okay, we load weight number B, and we can start by using the top right corner of our filter window, but when we go back to our partial sum in 1, 1, so we have to reload what we had stored over here before, and now we can multiply B by all these guys and by all these guys and add to our partial sum. Now we have two out of our 4 sums in each of these 1, 1 coordinates, and then we continue on to 1, 2 coordinate. We have 2 out of our partial sums, but we don't have to change the weight. So that's what weight stationary data reuse is. We're going to So we can look at these plots that show the reference pattern that we've been using. And these things are plotting this pseudocode over here that we have. So we have input activations that are of size H, filter weights of size R, and output activations of size E. And we're going over these loops that are running through our code, okay, calculating the output, which is weight times the filter. For these plots, we also took these numbers. So we have the input activation size of 12, the filter weight size of R, and the output comes out size of 9 through that. And what we have here in these plots is the x-axis is the cycle, so how we go along reading things and writing things and making the calculations, and the index of the outputs, the inputs, and the weights is in the y-axis. And what's clear from weight stationary is that our weights stay stationary. So that means we're going to use our weights many times without changing them, and we only actually have R 4 times we actually have to go and read new weights from the global buffer. Okay. On the other hand, with our partial sums, as you see, we have this fixed window that keeps on throwing out our partial sums and reading them again, throwing them out and reading them again. It takes E times our output reads and E times our output writes that we have to go to the global buffer. And for our activations, we have this sliding type of a window that keeps going up, down, up, down, up, down, up, down, and it's E times R input reads it totally throws out the inputs E times R times. So this is really good for our weights, but not that good for our partial sums and activations. The second type of data flow is the output stationary data flow, and this is going to be kind of similar to the input stationary. So here we're going to minimize the energy of reading and writing the partial sums versus beforehand we wanted to minimize the energy of just reading the weights. So this is maximizing the local accumulation of output feature maps and partial sums, right? Okay, so here what we want to do is we want to keep the partial sums inside our register files. Okay, and for that we're going to have to broadcast the weights to all of the filters, and we're going to try to stream the activations through the processing elements. So an example of this is Dian now. Okay, and what it does is it's actually doing this. It's using this type of an output stationary build inside its processing element feature here, which if you go over the paper you can read about that. So just before we start with output stationary, there are actually 3 variants of output stationary, what we call output stationary A. It's going to try and keep all of what we're doing in a single output channel at one time. Okay, and that's good for convolutional layers. We're going to try to store as many possible of these partial sums that are in one output channel before going to the next output channel. Okay, the opposite side of that is what we call output stationary C. That's going to try and have all the output channels in the partial sum registers at once, but and and then change them later on, and that's targeting fully connected layers. And then the output stationary B is kind of a mixture between them. We may have a good part of a single output channel, but we'll have several output channels at once. So there's any type of mix of this depending on the amount of storage we actually have in each register file, and the size of our the size and the number of channels in our output maps we have to take into consideration when building the structure out of these. So again, it's kind of hard to understand that without seeing the mechanics of this. So again, let's look at this type of a mechanical graph that will show us this. So what we're going to do again is we're going to have anything that's red here is inside the register, and here we're gonna keep the partial sums in the registers. So we don't want to move this. We want to stay on this 1 1. And in this case, what we're doing actually is the type C over there, where we're keeping all of the output feature maps across all channels inside the registers. Okay, so we're going to cycle through the input feature maps and weights, and we're going to do local accumulation of the partial sums. So we start over here, and again, it's the same exact position that we started the weight stationary. We have our input activations over here in A. We have our weights, all of our weights in the top left corner of our filter, and when we do our multiplication here, we're going to get the first partial sum of the top left corner of the output feature maps. Okay. Now what we're going to do actually is we're going to throw out our weights. Beforehand we kept our weights, and we're going to load new weights. And these new weights are going to multiply the top right corner of our window of interest, and that means we're actually coming in and filling in partial sum number 2. So we didn't have to change and throw out what we had in our accumulator here. So we just read what we had stored before from the register file and stored it back into the register file, but we had to replace our inputs and our weights. Okay, and again we're going to jump over and get the third partial sum and the fourth partial sum, and now we have the full product of the top left corner of our output map. So now what we're going to do is we're going to throw out what we have there and move over to the second coordinate over here, and again we're going to start multiplying the top left corner, and we're going to start multiplying this again. Okay, so this is made up of our second window of interest after we slid the window over, and so we're going to multiply again the inputs by the weights, and each time we're going to throw out the inputs and weights and keep what we had in our output. So looking at the mechanics of this again, here we have the outputs, the inputs, and the weights. What we're going to see here, okay, is that the outputs stay stationary. Okay, it's going to take a total of E times. We're going to have to write out the output feature maps, because as you see here, E is 9. So 9 times we're going to go over all of the coordinates of the output, all the values of the output map, and every time we have to write out the rest. We never have to read from the output buffer, because we always start from 0 and just write out when we have the full sum at the end. On the other hand, with the weights, we're going to have to again run through all the different weights. So we have a total of E times R weight reads, and we're going to have this sliding window type of thing for the inputs, and that's going to be E times R input reads. So this is really good for the output. So we have no output reads and only E output writes, and we have E times R input reads and weight reads. But it seems to be a little bit better in most cases than weight stationary. Finally, we have the input stationary, which is corollary to all the others. We're going to minimize the activation read energy consumption, and therefore maximize convolutional fmap reuse of activations. And this again, we're going to put the inputs inside our registers, and then we're going to unicast weights, and we're going to unicast weights to the inputs, and we're going to try to stream the partial sum spatially across the global buffer. An example of this is a recent example called sparse CNN or SCNN, and this is a type of an accelerator that manipulates the sparsity, and it uses input stationary to do that. Okay, I'm not going to go over the mechanics because you probably kind of understand what we saw already in the wait stationary and output stationary. But if we look at the reference pattern, what we're going to have here now is obviously the activations are going to stay put, and that means that we only have E times we have to read the new input from the global buffer. And then again, the weights we're going to have to read again like this. Okay, we're going to have to scroll through all the weights, and that makes E times R weight reads. And with the partial sums again, we're going to have to read them again like that, which is a total of E times R output reads and E times R output writes. Okay, so to summarize this whole thing, in all of the cases we had E times R max that we had to do. Okay, so we had to do E times R max. The question is how many of the other things we had to do. And for output stationary, we had to have E times R weight reads and E times R input reads, but we didn't have any output reads, which is really good, and we only had E output writes. For wait stationary, we had only R times we had to read new weights, but then again, inputs and output reads and writes, we had to do E times R times. And for input stationary, we only had to read inputs E times, but for weight reads, output reads, and output writes, we had to do E times R times. Okay, so again, when we're designing our accelerator, we should try to find out what's the best fit for our algorithm. But then there's the row stationary data flow, which is kind of an innovative way of doing it, which tries to maximize the reuse and accumulation at the register file level for all the types, for weights, activations, and partial sums. And the way it does it is by processing a 1D row convolution in each partial element. It keeps the filter weight stationary inside the PE, it streams the feature maps into the PE, and it does a MAC for each sliding window at a time, one memory space for partial sum accumulation. There's no overlap between the input feature maps between the different sliding windows. The input activations are kept in the register file and reused, and the 1D convolution goes through all sliding windows in the row. Multiple PEs complete a 2D convolution. So let's see how that works because it's pretty cool. So the 1D convolution, the 1D row convolution in the P is like this. Here's our input feature map on the left side. Here's our filter, and here are partial sums on the right side. Okay, so what we're going to do here is we're just going to look at one row in this processing element. So this particular processing element, it's a MAC with its register file, is going to only look at one row. And since we're going to look at one row, what we want to do is, since our partial sum has in a row, since our dot product in the row, it has 3 elements, we're going to have 3 registers for the filters and 3 registers for the activations and 1 register for the output. So basically, the first thing we're going to do is we're going to fill in these the first 3 elements of the input and the 3 weights in this row, and we're going to accumulate the top left corner here for the partial sum. So now we have in our input register, we have the whole row here. Here we have the first 3 elements, and we do the dot product between them, and we get the full row value of A over here. Okay, that's the full row value of A. It's not the full value of A, because the full value of A has to have this part versus this part, but it's the full value of the row convolution. Okay, now what we're going to do is we're going to keep our weights the same, but we're now going to shift our inputs. So now inside our input buffer we have BCD, and now we can do the convolution with our same row that we had over here, and now we're going to get the full row of B. So we can drive out the sum of the row before and just accumulate what we have for B. Okay, and finally we'll again shift over. We'll take in the next window of our top row here, keep the same weights, and now we calculate the sum of that row. Okay, so that's how we did a full convolution of the row. How does that work? So this is maximizing row convolutional reuse and maximize row partial sum accumulation in the register file. We didn't have to go and read more partial sums, and we didn't have to swap out weights, and we only shifted over. Basically, we only read each input activation once. So that's real nice, but how does it work to make a full convolution? Because that we didn't see. So here we take our first processing element that we saw before. So we have our first row with our first filter row, and that's doing this convolution over here. So it's taking this first row, the top row of the filter, and it's giving us the top row of the convolution, or at least part of the top row of the convolution. So what we're going to do now is take two more of these processing elements, but the second processing element is going to take the second row of both the input and the filter. It's also going to do a partial sum of the top row of the output. The third one is going to take the third row of the input and the third row of the filter, and again, it's going to do the third part of the partial sum over here. So what we have to do now is take the partial sums that came out over here, plus these, and accumulate them together and it will give us the entire sum of this top row of the output. Okay, we're going to now have two more of these types of things. So the second one is going to take these three rows, and it's going to give us the entire, what we're going to get in over here is this output of the second row. Okay, the third column of processing elements is going to take these three rows, and it's going to give us the bottom output, which is going to go over here. So we were able to get in total with this 3x3 type of a matrix of processing elements, we were able to nicely get the full convolution of the 3x3 output map. This actually maximizes the convolutional reuse. Let's see how. So first of all, filter rows are reused across the P horizontally. So filter row 3 was taken into all these three processing elements. So we can just broadcast it basically to all of these guys. And it doesn't have to change. And again, filter row 2 in these three, and filter row 1 in these three. F-map rows are used diagonally. So we have IF-map row 2 here and here, 3 here, here and here, 4 here and here. So again, we might have to only have it stored one time, and we can broadcast it to all of them. Okay, and partial sums, as we saw, they're accumulated vertically. So what comes out of here and here and here, we just have to sum them up together at the top of the column. So that's really nice, and that brings us to our last example. By the way, row stationary was used in EnICS, which is what Vivian Z's group came out with, kind of along with this tutorial. So the final type of data flow is kind of a non-data flow. It's the no local reuse data flow, and that's basically what we've shown for like a lot of the temporal architectures. So small register files are very energy efficient. They have low picojoule per bit, but they're very area inefficient. They're big, so they have large micrometer squared per bit. Okay, that means that if we put in a lot of these small RFs, we're not getting as much total memory density on chip. Okay, so instead we can do no local reuse, not use any of these this lots of local storage inside the processing element. Then we can maximize the storage capacity, and this can minimize the off-chip memory bandwidth. We almost never, we much less maybe have to go to the very expensive DRAM instead. So all area is allocated to the global buffer, and nothing is stationary inside the PE. So so we have much more traffic on chip, and we saw that traffic on chip is expensive, but it's several orders of magnitude less expensive than going off chip. And what we have is we have to multicast the activations, we have to single cast the filter weights and spatially accumulate partial sums. So the data movement on chip here is really expensive, but at least we don't have to go off chip because we have more memory density on the chip. An example of no local reuse is the DRAM chip, and what you can see here is we have these three buffers over here, and the whole thing basically is covered with as much memory as possible, which are these three buffers: the in buffer, the out buffer, and the synapse buffer. So that's all for this lecture. And again, it's heavily based on Vivian Z's tutorials at ISCAS and her paper in the Proceedings of the IEEE.